everyone, welcome to the tutorial, deep dive into the interprocedural optimization infrastructure. My name is Hideto. I will give you this tutorial together with Stefanos, Kuter, Shinji, Luofan, and Johannes. Here is the outline of this tutorial. First, we will explain what is interprocedural optimization and the reason why it is needed. Next, we will introduce existing IPO passes in LLVM. After that, we will go into details about inlining and Attributor. So let's start.
Hi, I'm Shinji. I'm this year's Google Summer of Course student. First of all, I'm gonna clarify what IPO is. In LLVM, transformations and analysis are executed through passes. There are some pass kinds. For example, immutable, loop, function, CallGraph SCC, and module pass. And we can divide them into two groups like this. The upper three pass kinds are intraprocedural, and the lower two pass kinds are interprocedural. Interprocedural passes can take two or more functions as a unit to consider. So, IPO is optimization that considers more than one function at a time. Next, let's see the definition of CallGraph. CallGraph is useful when we consider the relationship between functions in a module. CallGraph consists of nodes and edges. Nodes correspond to the functions in a module. An edge from A to B means that function A might call function B. So, these two call sites correspond to these two edges from A to B and from A to C, and this call site corresponds to this edge from B to C. We have already seen the word CallGraph SCC as the name of pass kinds. SCC stands for strongly connected component. SCC is a set of nodes such that every node in SCC is reachable from every node in SCC. For example, the set of green nodes A, B, and C is an SCC because there is a path from A, B, C, and A. There are another two SCCs, this orange one and this blue one. We can always decompose the nodes of CallGraph into some SCCs, in this case like this. And we can arrange these SCCs in a line so that all edges between different SCCs go in the same direction. In this case, all edges between different SCCs are marked with red color and all of them go from left to right. Let's take a closer look at IPO passes in LLVM. If you are interested in the implementation of IPO passes, you can find almost all of them under LLVM/rev/transform/IPO. Now I'd like to classify IPO passes into some categories according to their purpose or their logic. The first is inliner family. Inliner replaces a call site with a body of callee function. They are, for example, always inliner, inliner, and inline advisor. The second is passes that propagate information between caller and callee. For example, Attributor, IPSCCP, and info function others. The third is passes that modify linkage and optimize globals. For example, global DCE, global opt, and global split. And others. For example, merge function, open MPO opt, and hot call splitting. We will explain more detail of these passes later in this tutorial. Next, let me clarify why we need IPO passes, what benefits we can get from them. Inliner specializes the inline function with call site arguments. Such specialization would expose intra-procedural optimization opportunities. Inliner also saves jumps for a function call and the cost for saving registers derived from the calling convention. Such saving jumps lead to the improvement of instruction locality. Propagating information would prove some probability in a certain position, and other passes would benefit from the probability. By restricting linkage appropriately, we can improve other optimization, and we would reveal dead code and provide better information for ring-time optimization passes. As I mentioned, IPO passes are either module pass or CGSCC pass. Module pass takes a module as a unit, so it is the most general pass kind. In contrast, CGSCC pass takes a CallGraph SCC as a unit. SCCs are processed in the bottom-up order. In this example, CGSCC passes process the blue SCC first, then the orange one, and then the green one. When an SCC is processed, CGSCC passes have already processed all reachable SCCs from the current one. CGSCC passes are allowed to modify the current SCC and to add or remove globals. But they are disallowed to modify any SCCs other than the current one and add or remove SCCs. However, you can do some disallowed things in the initialization and finalization functions. Okay, let me get to common pitfalls. We have to take care of scalability, and we have to treat complicated linkages appropriately. As I said, IPO passes would expose other optimization opportunities, so we have to consider in what order we execute passes. Function call is not only call or invoke instruction. For example, there is a callback call. Furthermore, there are unusual functions such as variadic function and functions with complicated attributes like naked, byval, and inleg. We have to handle all of them properly. At last, IPO passes might change the call graph, and we have to keep them updated. But new and old pass managers use different structures to represent call graph. The old pass manager uses call graph, and the new pass manager uses lazy call graph. So we need to use different API to update call graph for new and old pass managers.
Hi, I'm Luofan, and I'm going to introduce the existing IPO passes in LLVM. The first one is the simple inliner, which is a CGSCC pass and will do bottom-up inlining. In this example, the use_for function called the function for, and after we run the simple inliner, the call to for is replaced by the body of for. The next pass is the partial inliner. Instead of replacing with a whole function body like the simple inliner, we only inline the hot region of the function. The hot region of the code is the part that is assumed to be frequently executed. And in this example, inside the function for, the true branch of the code is assumed hot, so that the partial inliner will do is that it will inline the true branch and cut the code part of the original function to a newly created function in the for.code. Next is the always inliner, which only handles functions that have the always inline attribute. It will be run even with the O0 argument with the LLVM passive disabled, and it will override the inline heuristic. As the example shows, the inner function has the always inline attribute and is inline in the function outer. We will go detail into the inliner of the LLVM later. The next pass is the IPSCCP, which stands for Interprocedural Sparse Conditional Constant Propagation. It is the interprocedural version of the SCCP pass. It will do constant propagation and dead code and branch elimination. Specifically, it will assume all blocks and instructions are dead unless proven otherwise later, and it will traverse the IR to see which part of the code is alive and which values are constant. In the example, we see that the first call to recursive, the constant 0 is passed, so the compare instruction is always evaluated to true, and the return value will thus be 0 based on that find node. So the argument of the second call is 0. Now that the return values of the recursive function is always 0, we can replace all call uses of the function to 0 and set the function to that the return of the function to be on depth, because we don't care about the return of the function anymore. And since the basic block 4 of the function is never accessed, it is eliminated by the pass. The next is the argument promotion pass. This pass will promote those by-point arguments to be by-value argument, and we can do this if the argument we are looking at is only loaded at the callee function. The pass will save information about the loads of the argument that can be promoted, and based on that information, it will create new function and insert such load in the caller. In the example, the function test contains only load instructions of the first value of p. So the argument promotion pass will load the value of it in the callee and pass the loaded value to the new callee. The info function attribute pass will annotate the function attributes on known library functions, and the example shows that the pass adds the no free and no unwind attribute to the malloc library function. The dead code elimination pass will remove dead arguments from internal functions. It will first delete arglist if no VA start is called, and then it eliminates the argument by assuming all arguments are dead unless proven otherwise. In this example, the return type of the function test is never used, and in the function test, the argument is only used by the return type, so the argument is dead and the pass gets rid of it. The next pass is the called value propagation. This pass adds the callee metadata to the indirect call site indicating potential callees. In this example, the functions that test select might call is determined by the select in the function, and the callees are selected between 4.1 and 4.2, so the passes add the 2 potential callees to the call site. The function attribute pass will deduce and propagate attributes and has 2 versions, which are bottom-up and top-down. In the example, the pass can use the non-known attribute of the function bar. First, in the first branch, the return value is determined by the return type of 4, which is non-null. And in the true branch, the return type 2 should not be null based on the get element ptr instruction. So since all the return types are not null, the pass will annotate the function as non-null. The next one is Prum exception handler pass, which will remove unused exception handling code. In the example, the for function has no unwind attribute, indicating that this will not cause any exceptions. So the pass will change the invoke to call and delete the exception handling label. The global DCE pass will eliminate unreachable internal globals. The pass will assume all globals are dead, searching out globals that are known to be alive and deletes whatever is left over. Here, the internal variable A is dead, but L1 is used and thus alive, so the pass will delete A and keep L1. The global value optimization pass will optimize global values. It will do various optimizations to the global values. For example, it will evaluate static constructors and optimize non-adjusted globals using constant propagation and dead code elimination. Let's see the example. In the first part of the code, the pass will do constant propagation. Since there is no stores to the global variable 4, the variable 4 is known always to be the number 4, and the load 4 function will simply return 4. Since the global value 4 is never used ever since, after that it will be deleted. But this does not work on external linkage because we have no idea whether the variable is stored in other translation units, so we can't do such optimization. The third part shows that this pass, the pass evaluated the static global constructor, which initialized the global value base to 5, so the pass replaced the ondef to 5 for the base value. The constant merge pass will merge duplicate constant together into a shared one. It will construct a map containing globals with the same content and later merge them together. Here, the global 4 and bar have the same content, though they are merged together, but the variable base does not have the local linkage, so merging it with 4 might cause error while linking, so it doesn't get merged. The next is the merge function pass, which will find the equivalent functions and merge them together. Basically, it will compare two functions, and if they are equal, the pass will try to merge them into one function. The pass can reduce the code size and avoid unnecessary optimizations to the same code. Here, the function 4 and bar are equal except the return type. 4 returns I64 type, while bar returns the pointer to I64. The pass can merge them together because the size of the pointer is equal to the I64 type. So the two functions are merged, and notice the useful function. The call to 4 is bit casted to match the original type. The OpenMP optimization pass will do various OpenMP specific optimizations. The other passes are not aware of the OpenMP runtime calls, and such optimization will be left to be done by this pass. The example shows the runtime call deduplication by this pass. The hot code splitting pass will split the code and the hot region so that we can improve locality. In the example, the function sync has attribute code, so meaning it will seldom be run, and so does the other content of the if block. So the pass split such code into a new function for code. The attribute is a fixed point iteration framework that can subsume many passes, and it is able to deduce various attributes aggressively and simultaneously. In this example, the attribute deduces attributes to different positions of the IR, for example at the function position and the argument position. We will talk about the details of the attribute later. Thanks.
Hi everybody, I'm Stefan's Baziotis, and in this part we're going to talk about inlining. This is kind of the same thing of what I talked about in the present and future of interprocedural optimization, which is the tech talk that we're giving this year, and I would suggest that you see that as well. So these are my info, please feel free to contact me for anything. So inlining is conceptually very simple. Basically we just replace a call with the body of the call function. It is also simple as the transformation. It's actually the decision of whether or not to inline that is difficult. Actually, it has been shown to be at least as hard as an abstract problem, which means that in practice there's no hope of solving it exactly. So what people have been using basically from when inlining was first introduced is heuristics. And so lately, of course, whenever there are heuristics, there is machine learning. One important question is, can we always inline? The answer is no. Usually we cannot inline because we don't have the function call. Like for example, we may call a function in another module or compilation unit, or maybe we call in a function from a shared library, or maybe we call a function through a function pointer, which is also how virtual calls are implemented. This is kind of more interesting because the set of candidates is usually constrained, so the compiler can do more stuff as part of a bigger set of optimizations called the virtualization. And I would actually highly recommend to see such talks if you're interested in that. But also we may not be able to inline because we have weird code structure. And so a useful example is a recursive function. So recursive functions are actually kind of difficult to deal with in inlining, and so different compilers treat it differently. So LLVM inline tail recursion, but it can inline full recursion. Let's now see the benefits of inlining. So the first benefit is that it removes the branching because of a call. So when you call a function, you basically move to another part of the code. That in turn may improve instruction cast locality. And so to give an example of that, imagine we have this foo function, and so this foo function has a who loop, and it calls this bar function, which is way up in the code. So see that foo is in line 150 and bar is in line 1. Okay, let's assume that this is the code placement of the executable. If we try to execute this loop, we're going to go to the for loop, then we're going to go into bar, and we're going to jump way ahead in the code. So possibly we're going to have an instruction cast miss. Then we're going to execute bar, and then we're going to jump back into the loop, and then we're going to have another instruction cast miss. But if we line bar in place, we're actually going to have the whole body of the loop, bar included, in a whole contiguous region. Another benefit is that it removes the save and restoring of registers, also function prologue and epilogue and that kind of stuff. So that depends on the calling convention and the platform and other kind of stuff. But basically a common heuristic is if the actual function code, the useful code, is less than 2 times the call instruction sequence, which is basically anything that you need to do to actually call the function, then just inline it, because it's supposed to have benefit. But the most important benefit of inlining that unfortunately a lot of people miss is that it is an enabling transformation. So it makes the work of other transformations and analysis more effective. To see a simple example, let's check here that caller calls callee, and callee is an internal function. And so callee gets A and B, and it does basically a sign division. Now if we try to optimize callee as it is, we won't be able to do anything more. Like, we know nothing about A and B. But if we actually inline in the place that callee is called, you can see that now A, B is not A and B, it's actually 10 and 3. So we can do this division in compile time, we can do constant folding there. And then we can propagate that into the return value. So you can see that the code of caller is actually nothing more than a return of 3 that we computed at compile time. Also, the code elimination hit because callee is an internal function, and it's only caller is a caller that it's actually called in only one place. So we just remove callee altogether because it was inlined already. So inlining also has drawbacks. And one important drawback is the code application. So for example, we may analyze code multiple times, and I mean the same code, because the same code, like a function might have been inlined in multiple places. And so you will analyze its code in multiple places, and it's actually the same code, so you're gonna just repeat work. That can lead to code size explosions, so the executable may actually grow, which may make load times slower and stuff. But most importantly, may impact instruction counts. So for example, if you see this code that I have on the right, it's similar to what we had before. But now bar is actually called conditionally. Okay, and so let's assume actually that code 1 is actually rarely true. And let's assume also that bar is actually a big function. So we may inline bar into place. But now, because we inline bar, we may actually make the for loops so big that it doesn't fit in the instruction counts. So every time we go around the loop, we may have a miss. And if code 1 is really true, we actually don't get the benefit of inlining that much. Now, it's important to note here that if bar is latency sensitive code, so for example, it may actually be called rarely, but when we do call it, we want to be extra hot, we want to be in the hot path, then that actually may be a good decision. So all depends in the situation. And so of course we might increase register allocator pressure because we might need more registers, because there's no saving and restoring of registers into the stack or whatnot. So the reliable ranges are extended, and so more pressure to the register allocator. Also, maybe we can discover more invariants, so we need registers to keep them. Let's now see how inlining works in LLVM. In LLVM, inlining is the most important enabling transformation, and so the idea is to put it early in the pipeline in order to enable other transformations. Now, in LLVM, the bus manager plays a big role in inlining, as in everything else. Inlining is a CallGraph SCC bus. So what this means is basically LLVM creates this CallGraph. And so CallGraph is basically a graph where nodes are functions and edges are from callers to callees. So if A calls B, there's going to be an edge from A to B. And what I would like to do is to pick an order to visit this graph. Okay. So for example, from sinks to sources. But if the graph has a cycle, you can actually pick an order. There's no order like that. So what it actually does is it separates the graph in SCCs in strongly connected components. And this graph of strongly connected components is a DAG. It's a directly acyclic graph. So you can actually visit it in a certain order. LLVM actually visits CallGraph SCC passes in bottom map order, which is from sinks to sources. And so if there's no cycle, basically the CallGraph SCC is just the same as not having computed the SCCs altogether. Any function is an SCC, If it has a cycle, you treat the SSCs differently. The other thing is that the pass manager interlaces function passes between the visits of the inliner to the functions, or I should say to the SSCs. Now let's say an example to understand that. Let's say that we have this code, so we have A calls B and C, so A is the caller, B and C are the callees, and so we have the CallGraph on the right. In this case, every function is an SSC. And so let's imagine that we try to run this sequence of passes. The trivial way that we could do that is to say, well, this is a CallGraph SSC pass. So let's assume that we go in this bottom-up order. Let's start from the sinks and go to the sources. So we would start from B then C, or from C then B, and then we go to A. And we will run the inliner there. Okay, so we'll run in this order the inliner, and we would be finished with that, and then we'll run mem to reg on each function separately without caring about the order, because it's not interprocedural yet. But that's actually the very trivial way. This is not what the pass manager does. So what the pass manager does, it says, oh yeah, I'm gonna run the inliner in this bottom-up order. So I'm gonna start with B. But instead of moving directly into C, I'm actually gonna run the function passes before I move into C. Okay, so in this case, it's gonna run mem to reg. So what this means is basically we don't run the inliner in like the whole CallGraph, be finished with that, and then start with the function passes. We interlace that. So the same happens in C, so when we visit C, we run the inliner there, then we run the function passes, and then finally we visit A. And we may find out that we inline B and C, we can align them, and then we run again the function passes on A. Now this has a lot of benefits, it has some drawbacks too, which unfortunately we don't have time to go over. Alright, so here is a list of papers mostly that were very influential in the world of inlining and actually helped me very much understand inlining better. So I would definitely recommend that you download the slides and take a look at them if you want to understand more. So thank you very much. Feel free to contact me on anything that you want if you want to ask a question or whatever. And let's now move to the next part. Thank you.
Hello, I'm Kuter Dinel. I'm going to talk about the Attributor now. So let's start with a quick overview. So Attributor is an interprocedural fixed-point iteration framework. It's currently capable of deducing more than 20 attributes, and we essentially update the states until a fixed point is reached. We have module and CallGraph SSC passes for both new and old pass managers. So why is the Attributor so powerful? So Attributor provides an easy way of adding new fixed point analyses, and we can connect analyses with each other during the fixed point iteration. And many of the existing IPO passes can be replaced by the Attributor. Some of these are the IPSCCP, ArgumentPromotion, dead argument elimination, and more. So let's talk about some of the details. We have something called LLVM IR positions. So these are essentially describe a position in the IR. These are the positions that we can make deductions for. So we have function return, we have the argument, we have the function. So essentially for these locations we can make deductions in the Attributor. And we also have the floating position, which describes anything else that doesn't fit to any of these 7 categories. So let's talk about the abstract state. We have essentially, we can think of this as 2 states that are glued together. We have one assumed state and we have known state. So the assumed state is the assumption that we make, and the known state is essentially is derived directly from the IR, and both of these states are actually propagated in the analysis. And once these are equal to each other, we have reached a fixed point state. In the abstract state, we have essentially 2 core methods. One is indicating pessimistic fixed point, which makes the assumed equal to known. At that point, we give up on our assumptions and we accept the known value. And we also have the indicate optimistic fixed point function, which sets the known as assumed, which essentially takes the assumed and for granted. So we have the abstract attribute, which is so what we call attribute here is importance. This is anything that describes the properties of the IR position. So these actually form the core of our deductions, and this could be an LLVM IR attribute. This could correspond to an LLVM IR attribute, but not necessarily. Essentially, the abstract attribute is the combination of IR position and an abstract state. To give an example to some of our abstract attributes, the ones that correspond to LLVM IR attributes are A non-null, A no capture, A align. I think there are some more that are not here now, and there are AAs that related to LLVM IR attributes, like memory behavior. Memory behavior, for example, could be could result in the read none or read only attributes being added to the IR. Right? And we also have things that are unrelated to the LLVM IR attributes, like AA is dead and value simplify, which essentially work hand to hand to make liveness analysis possible. And so we have some core methods in the abstract attribute that if you want to create an attribute that you have to implement. Right? We have the initialize function, which initializes the state with by examining the IR. We have the update method, which essentially updates the state. It can query other attributes by calling the getAA function of the attributor, which automatically tracks the dependencies, and it creates actually a dependency map behind the scenes that I'm going to show you. And we have the manifest function, which essentially uses the deductions that we have made within the attribute, and essentially it manifests them to the IR. So to give an example to the update function, we have in here we have non-null for the return position. So essentially this is for checking if the return value of a function is non-null or not. So to be able to do this, what we do is that we essentially go over all of the return values and we clamp them together. What I mean by that here is that for us to be able to return the function return as non-null, we have to look at every return value and we have to make sure that all of the return values are non-null as well, because if a return value can be null, if we cannot prove that it is not non-null, we cannot make sure that the return value is always going to be non-null. And we are also tracking the returns, the change status here. This is very important because if we only update the dependencies, the attributes that depend on this attribute to make their own deductions, if this state of this attribute have changed. If you return unchanged but the state have changed, you can get incorrect results in those attributes. So this is very important. And if you return changed when the state have actually not changed, you are essentially just wasting time by updating those dependencies, right? So this is actually the dependency graph that, for example, when you analyze the program, we can have. So this is actually, some of the edges are highlighted here. The highlighted edges actually form a cycle, right? So this is actually end up being an iterative cycle where states change, right? So let's talk about the different phases of the attributor, right? We have the seeding phase where we decide which kind of deductions we want to start with, but it is important to notice here that the abstract attributes can ask for whatever other attributes they need. So essentially seeding is just to start things off. And if you only see the signal attribute, you can see multiple attributes being created. For example, most attributes require liveness information. And we have the update phase where we update the states until a fixed point state is reached. And then at the end, we have the manifest stage where we transform the IR accordingly to the results of our analyses, right? Okay, so let's talk about some of the features of the attributor. Like, we have some performance related features, like we track multiple dependency types, required and optional. Normally you would have a required dependency type when you're using the data from the attribute that you're depending on. But if the data that you're getting, if the information that you're getting from that attribute is not useful at the moment, but you think that it might be useful in the future, you add an optional dependency type, and you receive the updates like regular. But if that attribute ever becomes invalid, if the assumption is invalid, you don't have to invalidate your own attribute, right? So this is actually useful for performance, right? So we have some great utilities for users. We have helper classes for generic deductions. We can combine different stuff together. I'm going to talk about that in a moment. And we have some helper functions for traversing, like assume live uses, instructions, and basic blocks. This is also very useful as well. And we have a uniform analysis by square API, like getAA for that I've talked about before. And we have some really good features for debugging, like selective seeding, which lets you only seed a single attribute, and that saves you it helps with the debugging a lot. That I'm going to go over that as well. And we have time traces, which help you optimize the compile time, right? So this allows you to look at how much time that is being spent on a certain attribute, and we're going to show that to you as well, right? So the helper classes for generic deductions. We can combine all alive return values into a function return lattice, essentially, and we can take all call sites and make deductions about the function. We can combine all call citing arguments into a function argument. For example, we can essentially take call site return values, call site constant ranges, and we can essentially combine that. We can onion all of those ranges together, and we can reflect that into the function argument. And to give an example, we have the A return from return values. This is for combining alive return values. And actually, to return to the example that I've shown you earlier in the update method, you don't actually have to implement that method, because we actually provide you with a template implementation. That function was actually a lie that we have told you to essentially make things a bit more clear. A return from return values do the exact same thing, but it provides a template implementation. So we actually provide some abstract states for common situations. Like, we have different integer states, we have like Boolean state, we have bit integer state. So we use the bit integer state for memory behavior. For example, one bit might represent like read none, other one can represent no write. And the Boolean state is actually what we would use for the non-null example, right? So it is either non-null or not, right? There's no other option for that one. So we have the selective seeding feature, which is essentially a very useful debugging feature that essentially allows you to specify a common list, some comma-separated list of attribute names that you want to seed, right? So if you just want to seed a non-null, you pass this argument. But of course, a non-null is going to ask for other attributes like liveness, right? For example, for the return value, we're only going to combine alive return values together, and you can also specify a specific function to seed, right? So this really helps with like amount of the debug strings that you get, right? So amount of logs that you receive at the end. So I find this feature very useful. So let's talk about our time traces. Right, so this is a feature that helps you visualize the amount of compile time that you're spending on something. This is without our time traces, and this is with our time traces. And our code is a bit recursive, so you get these some like long chains, right? So thank you for listening to me.
Hi there, my name is Johannes, and I'm going to recap a little bit of what we've seen and give a little bit of context towards future work. So we tried to give you an idea of what IPO passes there are in LLVM. We started with like what an IPO pass is, but we wanted to go through the most important ones that you can find and spend a little bit of time on the inliner, which is arguably the most important one, though also kind of the weirdest one, given that it transforms interprocedural problems into intraprocedural problems, kind of giving up on the idea of interprocedural completely. So why don't we see more interprocedural passes? And if you look at our tech talk, you'll see like the intra-procedural passes, so the passes that are look at one function at a time, outnumber the ones that look at multiple functions at a time by far. The problem partially is that there's a lot of pitfalls. As soon as you start going beyond a single function boundary, you're going to have to deal with things like linkage, and things like unknown callers, external calls. The call graphs are different in the different pass managers. Supposedly, like your context is bigger, so you might end up spending more time on problems, and so on and so forth. So there's a lot of things that could go wrong. But we're developing the attributor to hide most of the complexity, give the people easy ways to specify what they want to do and how they want to do it. And the way it is designed is based on a theoretical foundation, which is less ad hoc than other passes that we've seen. And it kind of already encapsulates a lot of the functionality that we have in other IPO passes. So the one crucial highlight is really this dependency graph idea, that you have all these different kind of sources of information, and they can talk to each other freely, and they are updated until a fixed point is reached. And the way, the reason we do this, reason we want to do this, is that you can deduce way better information if you run all these analyses at the same time instead of running them one by one, especially if you have loops, especially if you have recursion. And given that the attributor already takes care of linkage and allows you to specialize, internalize external functions that have external linkage, for example, or that have linkage that doesn't even allow you to do interprocedural optimizations, it really makes this problem way simpler and removes a lot of those pitfalls. At the same time, gives you this nice model that is better suited and stronger than what we are using right now. In a way, this dependency graph and this idea of a work list fixed point iteration breaks with the rigid pass schedule that we are using, and that is arguably bad. So the fact that we run these passes one by one in a specific order really comes with a lot of downsides, and the attributor breaks with that. It is, if you want, a new pass pipeline in itself, where everything is run at the same time, updated as it needed. I'm not saying there are not things we have to improve before we can actually enable it by default, but certainly we're on the right track. And one interesting thing I wanted to note here is that if you look at the phases that we have, the seeding, the update, the manifest, you see different really interesting options for the future. So we are looking at seeding only hot code paths, or things that we might need in the future. So if we come up with heuristics, maybe learned from a lot of data, to limit our analyses to these really important things, we'll still get the best information by going further and looking at the surrounding context as needed, but we'll minimize compile time. At the same time, talking about compile time, if you look at the update stage, because it is all happening inside these abstract attributes and abstract states, and none of the updates is allowed to touch the IR and actually modify anything, this is a perfect place to introduce parallelism in a compiler. And we can parallelize the update stage, saving a lot of time if you have huge single monolithic translation units. So if you do a Unity build, or you just have a certain number of files that are way bigger than the rest, in that case where you can't scale out naturally through multiple make jobs, you really can win by the fact that the design of the attributor splits the analyses from the manifestation. Finally, before we conclude and end this talk and start to take questions in case you're in the live recording at the LLVM dev meeting, I want to highlight that there are existing talks from last year, as well as a technical talk this year, 2020, that touch the same topic. So we have an attributor technical talk and an attributor tutorial in 2019, where we introduced the attributor. We had an interprocedural optimization panel that year as well, all of which are on YouTube. And finally, this year we talked about interprocedural optimization in a technical talk. All that said, if any of this sounds interesting to you, if you want to know more about all the features that we kind of alluded to but didn't really go into detail, if you want to look into working to improve these things, if you are looking for tasks, if you're looking for information, please feel free to contact us. We have usually weekly meetings, and you might have noticed that most of the people working on the attributor were actually students. Most of them were at some point Google Summer of Code students, and that is and we've grown as a community around it. And we have these meetings, we have task lists where we discuss and list things that have to be done. and we're always welcoming people that want to help, that want to be part of this. It is all done in upstream LLVM, so there is no downstream code to speak of, which is great. It is not enabled by default, but this is a great way for people to get a foothold into LLVM development, because it's also kind of different from the rest. It's more theoretical. It gives you like very small, well-defined tasks that you can work on in isolation, but they still fit in the bigger picture and improve everything surrounding them, because everything is interconnected. Now, that was our tutorial. I hope you liked it. We'll have a Q&A session now, and again, feel free to just reach out to us. Thank you.
Hi everyone, thanks for watching the tutorial and thanks for joining in for the Q&A session. So we're going to start with the question with most votes. So the question is how to get involved with the IPO and the attributor. What should the beginner start with first?
Okay. Actually, I have got involved with Attributor and LLVM community this year through Google Summer Code. I think any beginner, even if you're a newcomer to LLVM, can start working on the Attributor. At least you understand the concepts of Attributor. There are some open tasks of Attributor, and some of them are relatively easy and suitable for beginners to tackle for the first time. For example, implementing new abstract attribute detection, a small abstract attribute. Attributor is designed so that we can do such tasks easily. So they are good for beginners. Actually, my first task was such a thing. But there are hard ones in such tasks though. Other tasks are available, such as improving the helper function for generic deductions. And you can contact one of us to get the description of such tasks. Feel free to take part in Attributor team. Thanks.
Thanks. So moving on, how do you decide which branch is hot when inlining?
So deciding a branch. Okay, so there are several ways. Like there is an attribute for like hotness and coldness, which you could either add yourself in the C++ code by adding an attribute yourself, or it could also be derived from profile guided optimization, which is essentially instrumenting the program to derive information of how it performs in runtime. So that gives us information the next time we compile the program. Of course, this has some overhead because you have to have like a two-step compilation. But as I said, the programmer themselves can also add it manually. We could also propagate this information interprocedurally. So yes, anybody wants to add something to this?
Just a very small addition. On profile guiding information, Clang has actually a really good tutorial on something profile guiding optimization and instrumentation. So you maybe want to check that.
Okay, thanks. Moving on. Does it make sense to also support top-down inlining?
That's kind of a hard one. And in some sense, yeah, I mean, it makes sense in that you will have more capabilities, but how do you do that in a good way as far as implementation goes? So it's a little bit hard. I mean, at some point, GSoC had implemented a top-down inlining, and it went really bad. Although we may argue that it went really bad not because the method itself was bad, but yeah. So it may make more sense, kind of a hybrid approach, where it's not strictly bottom-up nor top-down, and it's like given some metrics, the inlining candidates are sorted in some kind of a queue. So.
Okay. Thanks. So are there thoughts on separating traversal of CallGraph to find inlining candidates and the inline order itself? For example, with PGO information, I may want to sort candidate list by CallGraph edge hotness.
Should I take this one?
Yes, go for it.
Yeah, okay. Yeah, so again, that's kind of related to the previous question. It's a little bit, at this point, you can't actually do that as far as I know in LLVM, because there's no real way to say, okay, I want to sort the inlining candidates with this metric, which, for example, could be, as you said, CGH hotness. So yeah, there's no such a thing. You would have to have more of a flexible approach, which right now really does not exist. We only have, as far as I know, bottom-up inlining with some capabilities for deferring inlining, but that's tricky too, and it's not really clear how it works, to me at least.
Okay, moving on. Are there any optimizations to change argument types? For example, only the low 32 bits of an I64 attached anywhere and the argument replaced with I32?
As far as I know, there isn't such optimization which can change the argument type. The argument promotion path and the attribute can change the function signature, but for now they don't support such transformation. I think we can use the attribute to do such optimization. For example, we can use the assumed value range of the argument, or probably the information about the bits used of the argument, which has not been implemented. I think the example of changing the I64 argument to I32 doesn't necessarily lead to better performance, because maybe in a 64-bit machine, we might still need to extend it to 64-bit. So that's probably target dependent. Anybody want to add something to this?
Yeah, I want to just to highlight this. Changing a function signature in LLVM-IR is not strictly speaking trivial. If you look at how that is done in argument promotion, you will notice that for various reasons, everything from updating the call graph to modifying COMDAT or like getting the COMDAT sections right, getting all the attributes right, things like that. So there's a lot of moving parts, like a lot of things you have to do to get it to change the signature of a function, even to just delete something. Now that said, to make that simpler, the attributor actually provides this function signature rewrite capability where you say, okay, I want to replace argument number 3 with the following set of types, and then you get certain hooks. You provide certain hooks that are called, so the attributor does the rewrite for you, hooks everything up, and your callbacks are going to be invoked in order to update the call sites and so on and so forth. So it kind of makes the task of writing a transformation like this way easier, because you don't have to worry about all the nasty details. Really, just about the fact that you said, I have this I64, and I want to replace it with the lower bits. So I'll tell the attributor I'll change attribute 3 from the existing type to a 32-bit type. And then every time I get to my callback is invoked for a call site, I'm just going to take the lower 32 bits, like I truncate it. And then I pass, like I tell the attributor that this is the new attribute to be used, argument to be used. And that makes this at least really like straightforward in the transformation side of things. You still need to do data and analysis yourself, but I guess that is part of life.
Thanks. So will the function specialization add to the code size?
Anyone want to take that one? Okay, I'll take it. The long answer is
sure. Oh, yeah.
And sure, it will, for all kinds of reasons, you specialize, which means you duplicate, which means you have more code and therefore more code in your executable. And the only reason why you want to specialize is more or less because the original has to stick around. Otherwise, you would have just kind of specialized the original. And so yes, it will probably impact code size. But at the same time, you can use it to avoid inlining, which at the end of the day is specialization per call site. So if specialization for a set of call sites is results in as good code as inlining would, more or less, you win. So for example, one way of specialization that we do in the attributor under a flag right now is to specialize for all the call sites in the translation unit in order to make function linkage problems go away. So literally you can think of that by we inline the function at every call site and then we outline it again and put it in like an internalized version of it. In that way, we get around non-exact linkages and can still do interprocedural optimization. But that is just kind of the most coarse-grained kind of specialization that is useful. From there on further, you could specialize for a set of call sites. For example, all the call sites that pass 5 as the second argument. Again, that might enable you to do exactly the kind of code simplification you need to get your performance, but it avoids to inline that kind of function everywhere where 5 is passed. So it is not easy to tell, and certainly we need heuristics to determine these things, but only with a heuristic, like a holistic view of the program, the ability to run these interprocedural optimizations under the assumption you did specialization or you can do specialization actually can lead to us being able to actually derive a proper heuristic here.
Stefanos, did you want to add something?
That's okay, thank you.
Okay, moving on. Is there any way to retrieve instructions or info about them in the caller that corresponds to the inline function?
So I'm not 100% sure I understand the question, but if you have a call and the callee is known, you can kind of follow that call edge and look at the instructions that are in the callee. And at the same time, the inliner kind of knows what instruction it copied over. So while you're still in the inliner, you know what came from the callee and what didn't. I'm not sure if that doesn't answer the question, feel free to ping us afterwards.
Okay. So have you noticed whether the kind of code benefits from IPO, say C apps versus the C++ apps, and if there is any way to take advantage of that?
Oh, yeah. Basically, C++ has a lot of code application because of templates. So I guess IPO will be effective compared to C code. And as an important point is linkage. For external functions, it is difficult to optimize by IPO. So we need to propagate information in the entire program. So we need to know the whole programs. So if there are a lot of external functions, we need to annotate some kind of LLVM attributes or more high-level language to do more good interprocedural optimizations.
Right, and again, we we can go into specialization here to solve a lot of the linkage problems, especially in C++ code, where specialization is a very good alternative here to inlining. While C code has usually less complicated linkages, which are easier to handle with RPO directly.
Thanks. So can you go a bit more into inlining and when recursion is a problem?
Yeah, it would be helpful to know how much time do we have left. Anyway, so it depends. Well, okay. Well, it depends on what you mean a problem for. If your compiler doesn't support a recursion, then from the programmer side, it's always a problem. So, which LLVM, for example, doesn't support any inlining or recursion except tail recursion. But so recursion is generally difficult to reason about. But also one thing that you have to consider is that recursion doesn't happen that often. So you can see that on benchmarks and test suites and stuff. I mean, well, it doesn't happen that often if you consider the cases of LLVM and what tries to target and that kind of stuff. So like C++ code, Fortran. But if you consider, for example, Haskell or Lisp or something like functional languages, then recursion happens all the time, and then you have to reason in a different way there, right? But the recursion doesn't happen that often. So now why inlining is a problem is more of well, it's a little bit technical. In the other talk, I said that it's easy to do the transformation. It is not that easy, but it's not the best problem there. We really don't have very good heuristics. The closest we have is the loop unrolling, which does make some sense, but it's not really clear that you have the same benefits. So.
Anyone wants to add something?
I mean, again, I'm not totally sure what the question is aiming for, but conceptually you can inline even if you have recursive functions, right? The question is, at what point do you stop? And it is unclear what you want to do, and so a lot of times our inliner, for example, just looks at the easier case of inlining recursive functions instead of trying to do it in a more generic way.
Exactly. Just as most common, because I'm mentioning loop unrolling a lot. If you think about if you say have a recursion that only calls itself 3 times, and you actually inline that 3 times, you would have basically a function that has its copy 3 times. And now consider what happens in loop unrolling, right? If you unroll the loops that runs 3 times, you're going to have the copy of the loop 3 times. So that's why it makes sense to have common heuristics, somehow at least.
Okay, so moving on. Is the diverse virtualization for C-style vtables structured with callbacks feasible in LLVM?
The comment here.
Absolutely.
Yeah, so I don't know very much about the virtualizations. I hope that in the slides I linked at least 2 talks that have happened in LLVM on the virtualization, but in general, yes, you can. So for example, one of the talks that I'm quite sure I have linked is from a talk from a person that works in the Microsoft compiler. And he basically tries to argue about the virtualization, which happens in virtual functions, but the code that he shows is actually C pointers, basically. So how you would do C-style virtual tables. So in essence, and the other thing to consider is there's no really a big difference when you come to LLVM AR, right? So when you have virtual functions and you have LLVM AR in the end, they almost look the same as if you would implement it in C, but it's just basically a high level abstraction.
Right. So we have a devirtualization pass. As Stefano said, at the end of the day, in IR, it doesn't make much of a difference where you're coming from. And now the question is, like, this devisualization pass is fairly specialized on C++ style vtables that we're building. But let's assume you build your own virtual table. You have a struct, you have function pointers, you build that struct, you pass it around, you read a function pointer out of it, you call it. Right now, that can be optimized already. If it turns out, if you can kind of break up that struct into its components and propagate the pointer to the call side, which makes it a direct call. If you cannot break the struct apart, you have a problem right now. Now, breaking structs apart, especially across function calls, is what argument-promotion does. And it is very, let's say, conservative and limited right now. And the attributor already has a privatization abstract attribute, which does pretty much the same thing, but approaches it from a different angle. And while it currently, the functionality doesn't completely subsume the argument promotion pass, it will eventually. So we have kind of functionality to break things apart. And then afterwards, you can propagate the function pointers. And even if you can't propagate them in a way that there is always a single one that you pass along and you know which function is called, and you therefore can make it a direct call, the attributor has an abstract attribute that is called potential values. And maybe Shinji can talk about that in a second. Or let's go, and Shinji, you want to talk about potential values for a second?
Okay. I added a potential value attribute, and that analyze the potential value of the such value. And for example, a value can take 2 or 3 values, only 2 or 3 values, and maybe some comparison is no more needed, and we can delete them. Yeah.
Right. And so given that we have this functionality that, given an SSA value, try to compute what SSA values could this have, like simplified, have at runtime, you could now implement a C function call devisualization by saying, okay,
yeah,
I have an indirect call here. You take the SSA value of the callee. You ask this existing abstract attribute for simplifications of this function pointer. And if you get any function out of this, like if the simplification maybe says, okay, it is either function foo, function bar, or this other function pointer thingy that I can't simplify any further, you could specialize for function foo and function bar at this point, right? So you could have direct calls for them if that is what you're looking for, or potentially like inline those things. So you can do partial devisualization at that point. And if it turns out that it says it is either function foo or function bar all the time, you don't even need the indirect call anymore. And then lastly, if it is dependent on your call site, eventually we would like to have the capability of specializing for the call sites, or like for a set of call sites, but we don't have that yet.
And just a small comment here, which is it was a great addition about partial devisualization. That's actually a lot of times the virtualization is not like, oh, I just replace with a single call. We might have candidates, and that should hint that there's also profile getting information starting to have a meaning there, right? Like, for example, if in some way you can say, well, this function is called way more often, then I'm going to specialize or inline that. Basically, you go back to hot called information.
Okay, thanks. So it looks like we have some more time left. So I'm going to ask something myself. So what are the plans for enabling the attributor by default?
It's a good one. I get that asked a lot. First, there's a couple of steps that have to be taken. The attributor is, as it is developed right now, is not tested in any CI system, which is the first just flaw. So we have to set up a CI, a build bot that runs the attributor, that enables it. It's in the branch. You can just enable with O3. So we just have to do that because, especially over the summer when we have GSoC, a lot of people working on it, we tend to introduce bugs. And right now I'm trying to kind of fix them and get them out, but we still have some. So certainly we have known bugs and we have a lot of unknown bugs. So after we had a CI and we are able to go through at least the regular codes that LLVM as part of its CI system runs without problems, we have to consider more codes that are maybe downstream for people. And then we also should take a look at a few other things. For one, the attributor has two modes, the module mode and the CallGraph SEC mode. There is a reasonable argument to be made we should enable only one of them, or at least for the beginning. So the module mode is somewhat easier, but has memory overhead that is non-trivial because it literally builds abstract attributes and it builds kind of a reasoning model for the entire translation unit, which can be a lot. And it actually reasons about everything at the same time. We are currently working on smarter schedules there. So even in the module pass, we could reason strongly connected component at a time, and then inside of them function at a time, and then try to throw away state that we don't need anymore before we accumulate too much. So certainly there's improvements on the way. At the same time, if we enable the CallGraph SEC pass that is that has less overhead in memory, less overhead in compile time, but still overhead in compile time. So it is not as bad as it was last release for sure. It's reasonable, but we can still push that down. And there's a couple of things that we could do to do so. For one, we're very aggressively kind of going for attributes right now. So whatever we can derive, wherever we can derive it, we will try to. So we will try to mark every single argument, every single return pointer, every single call site return, every single call site argument as non-null, non-null, dereferenceable, aligned, and so on and so forth. So we really don't have any heuristics in place as of now to limit where we seed these attributes. And certainly we could just reduce compile time by a lot by saying, okay, we're going to deduce alignment not for every argument, but for the loads and store instructions that we see instead of every argument. There's a little from a correctness perspective and actually testing things and trying things out, this made sense. But for a mode that is in release used, we really want to restrict it to the things that can benefit the program and then go from there. So these steps should be need to be followed one by one. And at the same time, obviously it's a moving target, but we certainly, what we'll need eventually is more testing. Okay, I think we're almost out of time. I thank everyone for listening in. We have a tech talk as well in case you missed that. It will be online. Slides will be available eventually. And we have the community.
Thank you very much, everybody.
Conversations. Sorry, Stefanos?
No. Sorry, I thought you finished.
Go for it.
No, go for it. We have 10 seconds.
Okay, thanks everyone. And talk to you later. Bye-bye.
Thank you.
Feel free to join the community board.